Hello there, and welcome back. In this video, we're going to continue our discussion of some of the common metrics that are used to describe samples and populations of statistical experiments. We already discussed some measures of central tendency and also some measures of position. In this video, we're going to be focused on measures of variation, and sometimes they're also referred to as measures of dispersion. So a measure of variation describes how spread out a value or set of values is in a data set with respect to one or many of the other elements in that data set. So to start, there are a couple measures of variation that are actually extremely easy to calculate. The easiest of them is going to be the range of a data set S. So the range of a data set S is going to be defined to be equal to the maximum element of S minus the minimal element of S. Although this is very easy to calculate, there are at least two big issues that the range has. And if you want to pause this video and think about what those issues are, feel free to do so. But the first issue is that it is heavily influenced by outliers. And why is that the case? Well, remember, outliers are typically extremely larger or extremely smaller than the rest of the other values. So they tend to be equal to the maximum and the minimum elements. So therefore, if you have an outlier, your range is going to be extremely different than if the set didn't have outliers at all. Another issue is it only depends on two values, which could be the outliers, but even if they don't, if they aren't outliers, it's still an issue. And you consider a couple scenarios where this is the case, right? Let's assume the maximum and the minimum element for these two sets are equal, right? So this is going to be set 1, and this is going to be set 2. So let's assume that the distribution of elements for this is something like that. So its range is going to be like 10. And also this data set will also have a range exactly to the other one because the maximum and the minimum elements are going to be the same. So even though the spread of the values is completely different, the range is still going to be the same. So the range has those two issues at least, right? So how can we fix at least one of them? So remember, in terms of quartiles, the range can be calculated as Q4 minus Q0, the difference of the outer quartiles. So maybe if we use the inner quartiles, we can at least fix the outlier issue, right? Of course, we're still only going to be using two values if we use the inner quartiles, but at least we fix one of the issues that the range has, right? And that gives birth to what we call the interquartile range. So the interquartile, or the interquartile range. And most of the time, this is abbreviated by IQR. So the interquartile range of a data set S is going to be the difference of the inner quartiles. So now it's not going to be as heavily influenced by outliers as the range is, but it still only depends on two values. So let's just do a brief example on how to calculate the interquartile range for a data set. So example, let's assume my data set is the set of numbers 3, 7, 10, 11, 13, 15, and 20. So remember, to find the interquartiles, there's a couple variations for this, right? So notice that there's 3 elements to the left of 11 and there's 3 elements to the right of 11. So what I'm going to do is I'm going to use the exclusive interquartile approach. So if I use the exclusive interquartile, I'm going to partition this into 3, 7, and 10, union 11, union 13, 15, and 20. So I'm not going to include, I'm going to exclude the median from the left and the right hand set, right? And keep in mind this is a ranked set already, so that's good. So 7 is going to be Q1 and 15 is going to be Q3. That means the interquartile range is going to be the difference of these two. So that's going to be 15 minus 7, which is going to be 8. So that is my interquartile range for this particular set. Now, yes, it is fixing the outlier issue, but it still only depends on two values. So does that mean that the interquartile range is useless, so it might be useless in terms of a measure of variation, but maybe, since it's not affected by outliers, it can help us determine whether a value is an outlier or not. And that's one of the applications of the interquartile range. So let's get into that briefly. So this is going to be called the IQR Outlier Test. Okay, so how the IQR Outlier Test works is it compares all of the data values to what we call a determination interval. And the determination interval, so determination interval, which I'm going to abbreviate by fancy letter I, is going to be defined to be equal to Q1 minus C times the IQR, and then Q3 plus C times the interquartile range. And this C number is what we call a threshold constant, or a sensitivity constant is another word. Threshold constant, right? And it's determined by the population distribution. So determined by population distribution. Now we're not going to be determining, which value of C is most appropriate for a population distribution, or, what if we only know a sample? How can we infer anything about the population distribution from that, right? We will explore this problem a little bit later. Well, not a little bit later, actually a long time later. But for now, let's just assume that this threshold constant, this sensitivity constant, is going to be given to you. And some common values. So some common values for C are 1.5 and 1.7. These are usually associated to what we call normal distributions or symmetric distributions or bell curve distributions, if you've heard of them. But we're not going to get into where these numbers and how they're sort of connected. Usually these values are going to be given to you, and then you have to construct your IQR outlier test determination interval and then go from there. So let's do an example of how we can use this and see if a set, and let's use the same exact set as before. So let's use S is equal to 3, 7, 10, 11, 13, 15, and 20. So remember, Q1 came out to be 7, Q3 came out to be 15, and then from these two we found the IQR to be equal to 8. So let's let our threshold constant be equal to 1.5. So some people will call this the 1.5 IQR outlier test. Right? So if that is the case, then our determination interval is going to be equal to Q1, 7, minus 1.5 times our IQR of 8, and then 15, Q3, plus 1.5 times our interquartile range of 8. So 1.5 times our interquartile range is going to be 12. So our determination interval is going to be equal to 7 minus 12 and 15 plus 12, which is going to be equal to minus 5 comma 27. So this is our determination interval. So what do we do with this? So we look at all of the elements and see which elements are not in this interval. We'll also notice that since 3 is in this interval and 20 is in this interval, all of the other elements are also going to be in that interval as well, right? So that's one of the easy checks that you can do. So therefore what? So if our threshold constant C is equal to 1.5, then S does not have any outliers. So keep in mind, if we change this value of C to like 0.1 or something really small, then this interval becomes extremely more narrower, and then some outliers will come into play, right? So it really depends on what threshold constant you choose, but that is the basic idea of IQR outlier detection, or the IQR outlier test, and just a brief discussion of this sensitivity constant, this threshold constant, and where it may come from. But we'll get into how to calculate that a far time in the future. But for now, let's just assume that is going to be the case. So we have two measures of variation so far: the range and the interquartile range, and also an application of that. So now let us look at a few other measures of variations that are commonly used, and maybe we can overcome both of the downsides that the range had. So the next measure of variation that we're going to be looking at is going to be referred to as the sum of absolute differences. So the sum of absolute differences, and some people will just abbreviate this as SAD, S-A-D. So the sum of absolute differences for a data set S is going to be literally the sum of absolute differences between the values of the set and a measure of central tendency of your choice. Typically, we use the arithmetic mean. If you're scared of outliers in your set, you may want to use the median for this, right? But by default, the sum of absolute differences is always comparing values to the arithmetic mean or the average. So what this particular measure variation does is it measures the total distance of how far each of the elements are with respect to a particular point. And in this particular metric, we're comparing everything to the arithmetic mean, or the median, or the mode, or one of the quartiles. It doesn't really matter, right? So that's what this type of metric does. So let's actually go through an example of how to calculate the sum of absolute differences for a particular data set. So let S be equal to, let's do a baby set. 1, 2, 3, 4, and 5. So we can quickly see that the average is going to be equal to 3, right? So the sum of absolute differences for our data set S is going to be the absolute value of each of these elements subtracted from the mean and then added all together. So this is going to be 1 minus 3 plus the absolute value of 2 minus 3 plus the absolute value of 3 minus 3 plus the absolute value of 4 minus 3 plus the absolute value of 5 minus 3. So that's going to be equal to the absolute value of negative 2 is 2 plus 1 plus 0 plus 1 plus 2. So that's going to be 4 plus 2. That's going to be equal to 6. Now, if this set contains a lot of large numbers, this number tends to be a little bit large, right? And also, since we're using the mean is more affected by outliers than the median, but it's better than the mid-range, right? So at least we have some outlier tolerance, I guess you could call it. And also we're using all of the values, so all of the values are accounted for. That's good too. So the sum of absolute difference at least overcomes the two issues that the range has. But this number tends to be a little bit large. So is it possible that we can make this metric a little bit better? And the answer is, of course, yes. So the next measure of variation is a modification of the sum of absolute differences. And this is called the average of absolute differences. Some people will also call this the average absolute deviation. Regardless of which term you use, it's abbreviated by AAD, the AD. Okay, so the average absolute deviation of a data set S is going to be equal to the sum of absolute differences of S divided by the sample size M. So that's going to be equal to 1 over n times the sum from k is equal to 1 to n of the absolute value of xk minus x bar. And some people may even write this as the sum from k is equal to 1 to n of xk minus x bar all over the sample size n. That's equivalent to. So if we continue our example, so our example continued, this is going to be equal to what? So that means the average absolute deviation of S is going to be equal to 6 divided by our sample size. So remember we have 1, 2, 3, 4, 5 values there. So that's going to be equal to 1.2. Notice that dividing by 5 makes our number a little bit smaller. Now, the absolute value function, in case you aren't aware from calculus, is not differentiable at its vertex because it has a corner there. So if you want to maximize or minimize a function that's not differentiable at a point, it's sometimes a little bit difficult. So this is one of the reasons why, and it's not obvious at all, right, that the average absolute difference and the sum of absolute difference is actually not an ideal or perfect, whatever that means, metric for representing variation or dispersion in a data set. So the next measure of variation sort of tries to fix this. And this is going to be called the sum of squared differences. So the sum of squared differences, this is going to be called SSD. Right? So solid state hard drive or something like that, right? So this is going to be defined, so SSD of our sample set S is going to be equal to the sum from k is equal to 1 to n of xk minus x bar, the quantity squared, right? And keep in mind, these are all for samples because I'm using little n and x bar. If you're working with populations, you should know how to write that. So that's going to be SSD of p is going to be equal to the sum from k is equal to 1 to capital N of xk minus mu, the quantity squared. So that's the population representation of it, but no differences really, right? So how would I calculate the sum of squared differences for a data set? So actually, let's work with a population this time. So let's assume our population set is going to be 1, 2, 3, 4, and 5. And we clearly see that the population mean mu is going to be equal to 3. So therefore, the sum of squared differences for my population P is going to be equal to, so we're going to take all the values, subtract the mean, and then square that difference. So this is going to be 1 minus 3 the quantity squared plus 2 minus 3 the quantity squared plus 3 minus 3 the quantity squared plus 4 minus 3 the quantity squared plus 5 minus 3 the quantity squared. And that's going to be equal to 2 squared, which is 4, plus 1 squared, which is 1, plus 0 squared, which is 0, and then that's going to be 1, and that's going to be 4. So we have 4 plus 4 is 8, plus 1 plus 1 is going to be 10. So that is going to be the sum of squared differences for this set. Now again, keep in mind, this number will be even larger, usually, than the sum of absolute differences for the set, because instead of just subtracting, now we're squaring those differences. So this is usually going to be even larger. So you may think, okay, well, maybe I can just divide by a number and that will make it smaller. Yes. And there's also another step that you need to consider, because there's a downside to this that might not be obvious. So remember, let us assume that each of these represents a length of a fish or something like that. So maybe these are in centimeters or meters or something. So if each of the elements are measured in centimeters, then the mean is also going to be measured in centimeters too. So we have centimeters minus centimeters. That's each of the differences is going to be centimeters. But when we add up all those squares, this is actually a squared centimeter unit. So the sum of square differences isn't even in the same unit as our data set is. So this is actually really bad. So what we can do is we can make it smaller by dividing by n or something, and then take the square root of that number, and now we're back in the unit that we used to be in. And that's what the next few measures of central tendency take into consideration. So the next is going to be the variance. So the variance is pretty chill. So the variance, which I'm going to represent as VARP, and also there's going to be a fancy notation that we're going to use for the variance of a population. That's going to be sigma squared. So sigma squared. So sigma squared is going to correspond to the variance of a population. So this is going to be equal to the sum of squared differences for a population divided by the population size. So this fixes the largeness of the number. And what if we have a sample? Well, is it the same calculation? The answer is no. Now this is very, 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 very important, right? So this is going to be the population approach. Now how are we going to do the sample approach? So there's a very subtle difference, and I'm not going to get into the proof why we want to do this. But the variance of a sample is going to be equal to s squared. That's how we're going to notate it and differentiate between sigma squared, the parameter, and s squared, the statistic. This is going to be the sum of squared differences for the sample, all divided by sample size minus 1. And again, I'm going to prove why we want n minus 1, not n. Of course, it makes it not as small as dividing by n, but it's still making it smaller. But there's a really good reason, and it's because these two things need to be related in some way in order for it to be good, a good estimate for the parameter. So if we continue our example from before with the population, so example continued, So that's going to be equal to what? So sigma squared is going to be equal to our sum of square differences, 10, divided by our sample size, 5. So we're dividing by 5. Why? Because we have a population. If this was a sample, we would be dividing by 5 minus 1, so we would be dividing by 4. But that gives us 2 as our variance for the population. But again, keep in mind, the variance, again, is not in the same units as our data. It's in the squared version of the units. So how can we fix that? We just take the square root, and that gives birth to the last measure, or not the last measure of variation, but a very important measure of standard variation known as the standard deviation. So sigma, some people will write it as STDEV of P, is going to be equal to the square root of the variance of the population. Similarly, the standard deviation of a sample, or STDEV of S, is going to be equal to the square root of the standard deviation of the sample. And if you want to write the formula out, sigma is going to be equal to the square root of the sum of xk minus mu squared divided by capital N, and the sum ranges from 1 to n, capital N, and S is going to be equal to the square root of the sum from 1 to little n of xk minus x bar, the quantity squared, all over n minus 1. So those are the formulas. So in order to calculate the standard deviation, first calculate variance and then take the square root of that. So if we continue from our population example, right, then the standard deviation is going to be the square root of 2, because 2 was our variance for our previous example, right? And that's going to be, if we want to decimal, 1.4142, if we really want it. Okay, so that is a few measures of variation. But recall there was another measure of position that we discussed. It was called the difference score. So let's just bring that up. So a difference score, this was a measure of position, and it talked about the distance a particular value is from the mean. And notice we're actually doing a couple difference scores in all of these absolute differences, sum of absolute differences, square differences, variances, and standard deviations. They all have different scores in them, or different scores in them. So that's pretty neat. So remember, the difference score for a particular value x is going to be x minus x bar for a sample, or dx is equal to x minus mu for a population. So another measure of position, that we can add to our list is what we call a z-score. So a z-score. So a z-score is defined to be equal to the difference score divided by the standard deviation. So dx over s for a sample, or dx over sigma for a population, right? And we usually abbreviate these by z sub x. So z sub x is equal to d sub x over s, or z sub x is equal to d sub x over sigma. And we can, of course, expand this. So z sub x is going to be equal to x minus x bar over s, or z sub x is going to be equal to x minus mu over sigma for a population. Right, so those are a couple other measures of position that we can add to the list. And remember, if x and x bar are measured in centimeters in standard deviation, also measured in centimeters, this is a unitless measure of position. So it has no units associated to that. And what else can we talk about? Well, there's another measure of variation that we can discuss that relates measures of central tendency and variation together. And this is called the coefficient of variation. And this is also another unitless measure of variation that is commonly used. So the coefficient of variation for a sample is defined to be equal to the standard deviation divided by the sample mean, or for a population, the coefficient of variation for a population is going to be equal to the standard deviation of the population all divided by the population mean. And keep in mind, this is again unitless. So if you want to compare the heights and the weights of a particular animal, and you want to see, okay, which one of them has a larger dispersion or a larger variation, they're not in the same unit, so you cannot compare their standard deviations directly to each other because the units aren't the same. So what you can do is you can calculate the coefficient of variation for both of them and compare them because they do not have any units associated to them. So these are all of the common measures of variation, and that gives us a set of different metrics for each of these measures: position, central tendency, and variation, that are commonly used. So since those are the basics of statistics, in the upcoming videos we'll just mention a couple more things, a couple different representations for data sets that are commonly used. Also do a bit of how to calculate these things in Excel if you have a large set of data where you don't want to do these things by hand. And later we're going to get into some of the applications where we can actually use these and make inferences about the population from them. So I look forward to seeing you there, and I hope you have a wonderful day. Take care.